Okay, let's see question 10. The president of the college asked the fraternity to submit a list of 7 students to serve as guides at a school function. They have 19 students who are available to help. So this is choose 7 out of 19. In how many ways can the students be chosen? So we ask ourselves, does the order matter? Right, we want to choose 7 students to serve as guides. So its order does not matter. So that's combination. Out of 19, choose 7 of them. Remember that's permutation. Out of 19, permute 7, then divided by 7 factorial. So if we do the calculation by permutation, we get 19 times 18 times 17 times 16 times 15 times 1, 2, 3, 4, 5, 6, 7. So we permute these 7 numbers starting from 19. Then we divide it by 7 factorial. 7 factorial, which is 7 times 6 times 5 times 4 times 3 times 2 times 1. Of course, you can use a calculator to do this, all right? For me, I can simplify some. So 2 times 7, that's 14. Simplify this. Then 3 times 6, 18. Simplify this. Then I have 4. 4 divides 16 by 4. I have 5. 5 divides 15 by 3. So we're left with 19 times 17 times 4 times 3 times 13. I use my calculator. Do 19 times 17 times 12, because 4 times 3, 12, times 13. I get 50,000, so the number is 50,388. So there are 50,388 ways of doing that. Okay, but it's combination. So remember, the order does not matter, so it's a combination. Okay, that's number 10. Now let's look number 11. Lucy was born on June 10th, 1969. How many 8-digit codes could she make using the digits in her birthday? So how many digits in her birthday? 0 is there, 1 is there, 6 there, 9. 4 digits, right? 0, 1, 6, 9. That's it. So 4 digits. 4 digits there. So how many 8-digit code? So 1, 2, 3, 4, 5, 6, 7, 8. 8-digit codes could she make using digits in her birthday? Well, it didn't say can I repeat, or didn't say anything. So we just assume it can be repeated. All right. So the 8-digit codes, the numbers can be repeated. It's like we could have 1, 0, 0, 0, 0, 0, 0, 0. Or maybe we can even have 0, 0, 0, 0, 0, 0, 0. Like that, because there's no condition here. So for the first one, how many choices we have? We have 4. Second one, we have 4. So for all these 8 digits, 8 places, we have 4. By counting principle, what do we do with those numbers? We multiply them. So basically, we have 4 raised by 8. Well, 4 raised by 8 is 4 squared raised by 4. Well, 4 squared is 16. The 16 raised by 4. 16 squared is 256. 256 squared. 256 times 256. So we get 65,000. 536. Right? Because there's no condition on this. Okay, so for each one of these 8-digit code, we have 4 choices out of those 4. And those 4 are the digits from Lucy's birthday. Okay, let's see 12. Suppose a jar contains 17 red marbles and 32 blue marbles. If you reach in the jar and pull out 2 marbles at random, find the probability that both are red, right? Remember, probability of 2 red equals to desired outcomes. So how many desired outcomes? Then divided by sample space. How many marbles we have in total? Okay, let's do step by step. So we recognize this is a conditional probability, right? Conditional probability. So let's see, probability of the first one red. Well, total we have 17 red, right? 17. Out of how many? 17 plus 32, 49. Right, total marble. 17 red, 32 blue, add together. So we have 49 marbles in the bag. And because 17 of them are red, so the probability of getting the first one red is 17 out of 49. Because we pull out 2 marbles, right? So the first one, probability the second one is red. Now, how many marbles in the bag? 48, because 1 is already out. So 49 minus 1, 48. And how many red marbles there? 16. Right, because we already consider here, first one to be red. So the second one, we have 16 over 48. Now, probability of the first one red and second one red. Remember, probability of A and B, 2 events, equals to probability of it. The first one, 17 out of 49. Multiply by, this is 9, multiply by 16 over 48. So what do we get? So 17 times 16, we get 272. And 49 times 48, we get 2,352. Well, this can be simplified. So we divide by 2, still even number, divided by 2 again. So let's see. So if you divide by 4, the denominator gets 588. Then let's see, 272 divided by 4, we get 68. Well, both are still even numbers. So 68 divided by 2, we get 34. 34. Then 588 divided by 2, we get a 294. Still even numbers. Keep reducing, keep dividing by 2. So 34. 34 divided by 2, of course, 17. And 294 divided by 2, 147. That's it. We cannot simplify further because 17 is a prime number. And 147 cannot be divisible by 17. So we're done. Wait. Let's see, 13. The table given shows the number of survey subjects who have received and not received a speeding ticket in the last year. Other color of their car. So we want to find the probability that a random chosen person got speeding ticket given they do not have a red car, right? Remember, probability of B given A, right? Conditional probability. So what is that? So we have to look for A first. What's A? Given they do not have a red car. So we go to this one, not having red car. How many in total? 515. So the denominator is 515. Now, among those, how many do receive speeding ticket? How many do receive speeding ticket? 45, right? So that's it. 45 divided by 515. Then we can simplify. 45 divided by 5, we get a 9. 515 divided by 9, what do we get? We get a 103, isn't it? 515 divided by 3. No. 515 divided by 3. I don't know what's going on. 515 divided by 5. Of course it's divisible. Yes, 103. So I'm right. 103 is not divisible by 3, so we're done. So the probability of a person do receive a speeding ticket given he does not have a car is 9 out of 103. All right, 14, last question. Compute the probability of randomly drawing 5 cards from a deck and getting exactly 2 kings, right? We draw 5 cards. 1, 2, 3, 4, 5. Remember, a deck of cards are 52. So our sample space is 52, right? And getting exactly 2 kings. So only care about getting 2 kings. So this is a king, this is a king. Doesn't matter, the order doesn't matter, right? The order does not matter. So as long as 2 kings. Okay, let's figure out this. So probability of getting the first one to be king. First king. That would be 1 out of 52, right? Then probability of the second one to be king would be, oh, hold on, not 1, right? Because we have 4 kings. So it will be 4 out of 52. But the second king will only have 3 out of 51. Then the rest of 3 doesn't matter. The rest 3 just choose. So 3 cards. So any 3 cards, right? I didn't see anything. So get 5 cards. But we only care about 2 kings. So the rest of 3 can be anything. So the rest of the 3 could be this one. The third one, I should say third one. So third card could be anything. So how many? Just 1, right? Just 1. Just 1. So this one, the probability of getting any card out of 50, we only have 50 cards left, right? Can be any one. So that's 50 out of 50. Then 49 out of 49. Then 48 out of 48. So we don't have to consider that. Because it's any card, right? So the only thing is we have to consider those 2. So the probability of getting 2 cards, getting 2 kings, 2K, right? Is 4 out of 52 times 3 out of 51, which is, this we can simplify, that's 1 over 13. So we get 3, actually this we cannot simplify. Yes, we can simplify, because 5 plus 1 is 6. So 6 can be divided by 3, so 51 can be divided by 3. I think that's 17, right? So this is 1 out of 17. So then what do we get? The numerator 1 times 1 is just 1. The denominator will have 13 times 17. We get 221. And that's it. So the last one is a little bit tricky because usually we say, okay, we randomly draw 2 cards, right? What is the probability of getting these 2 cards to be king? But this one, this scene, we just draw 5 cards. However, we only care about 2 to be the king. The other 3 can be anything. So it's exactly the same as saying, okay, randomly drawing 2 cards, what's the probability of those 2 cards to be king? Okay, that's it. That's all. That's all the questions similar to exam 2.